Okay, welcome back to part 2 of today's lecture. Thank you so much for being here. So now we're going to look at the fossil record and whether or not it supports the theory of evolution. So the theory of universal common descent is the idea that all organisms present today came from a single organism in the extreme distant past. Okay, this is not too terrible, and a common textbook type diagram or cladogram would be like this, where it shows the common roots that are actually missing. These are drawn in. And then the actual fossils that we have, which are these black dots. And this isn't obviously technically accurate, but it's a good illustration to kind of show what you would see in a normal textbook for universal common ancestry. So you had your bacterium way down here, and it evolves to your prokaryotes, and then your archaea, and then maybe your true eukaryotes and fungi, like they branched off, etc., etc. Well, if we look at just the fossil record and we don't draw in any lines, this is what it actually looks like. Okay, and this is looking at phyla, not every species. So that's why there's fewer lines. If you were looking at every single species, there'd be too many to count. But the major animal groupings or organism groupings look like this. The Precambrian, you have a very small number, one phyla perhaps, maybe two. And then immediately after the Cambrian, you have what's called the Cambrian explosion. You have almost every known phyla known that came into existence during the Paleozoic era. Okay? Interesting stuff. And so in a normal textbook, you would see a diagram like this to represent universal common descent, where your single-celled bacteria is here, and all of the lines are drawn in to show how things connect. Now, how accurate is that kind of diagram? It's a great question, and we'll look at it in a little bit. So the fossil record is conditionally plausible. Okay, and so what it shows is what could be. We don't know what is, and so we follow the principle of parsimony, which is the simplest explanation, is the one that we're going to go with. But that doesn't mean that's exactly what happened, because we don't have all of the pieces for the fossil record. It's deeply fragmented. Okay, and so one of the best series that is used for evolution is the whale series. When I was a kid, whales were thought to be organisms that had evolved in the water, and then they moved on to land. Okay, kind of like fish to reptiles. Well, we've discovered recently that it looks like whales came from land-dwelling animals in evolutionary terms. Okay, and so you have all of these different organisms that are thought to be related. Whether or not they in fact are related is entirely unknown. They look like they could be, right? Because scientists have very carefully picked the organisms that looked like they could fall in about the right order. But, this one could be an evolutionary dead end. This one could have been a dead end. This one could have been from an entirely different evolutionary tree that we know nothing about. It's just conditionally plausible. It's not actually true in the sense that we actually know without any doubt what happened. So another way to look at that is that the fossil record does not support evolution per se, because it's too fragmented to really support anything. It just fails to falsify. It fails to show it as wrong, because there is a general trend in the fossil record from simple to complex. But it's not the trend that Darwin thought, right? It wasn't a slow branching tree of life. It's rather sudden appearance and then stasis is kind of what we see. And that's why the theory of punctuated equilibrium came into existence, because the fossil record just didn't support gradualism. So let's look at some of these weaknesses in the fossil record. I've been kind of tossing pot shots as I've gone along. The first one is obvious. The fossil record is incomplete, like laughably incomplete. It's incredibly fragmented. Okay, and so if you take that first diagram that we looked at and you remove all of the lines that were drawn in, you have spaces. You have a dot here, dot here, dot here. These represent fossils over time. And the blank space is blank space. We don't know what's in between. We don't know if they connected at all. We don't know how they connected. We draw those lines in. Those are assumptions. Those are not proofs, right? And so if we took our diagram like this, there's a connection here. There's a little connection here, an intermediate fossil. And there might be, I think I saw one over here as well. It's highlighted. But if we remove everything that we don't know, it looks more like this, right? Here are all the lines, and then the lines that are drawn in are the assumptions. Now you tell me, is that a lot of assumptions? Well, it looks like it to me. And there are assumptions that are made because the fossil record is horribly fragmented. And what diagrams like this, even this, don't show is that this lineage probably was originally found down here. It's a ghost lineage, right? So the first fossil is here. They assume it exists up here, but it wasn't. You have a ghost lineage, meaning that the ancestor is oftentimes found before what it was supposed to have come from. That's pretty common. So they just kind of draw in the fact that it was an ancestor or a precursor, right? So they make it an offshoot and they just kind of draw it in. So there have to be a lot of ad hoc adjustments to what is actually there to make it look like it supports the theory of evolution. The next issue is sudden appearance. We talked about the Cambrian explosion already, and in a geological instant, you go from simple worms at most, fertilized sponge embryos, the echinoderms, which seem to have existed and then vanished. We don't know why. And then all of a sudden, you have a rapid diversification of basically every known phyla, with things like bilateral symmetry, body segmentation, essentially appearing out of nowhere and then staying pretty much the same until they vanish from the fossil record. Okay, and so if the history of life is a football field, this is the Cambrian explosion. It's geologically a very small amount of time, and again, you have every major phyla group appear very suddenly about 550 million years ago. Why? What was special about that? Why would that cause so many things to diversify so rapidly all of a sudden? We don't know. It's a great question. And so again, Cambrian explosion is a pretty big issue, and it was an issue that was known by Charles Darwin himself. And if you read his book on the origin of the species, then you will see that he offers the Cambrian explosion as one of the weaknesses in his theory. But he expected that we would find fossils below the Cambrian that would eventually lead up to the Cambrian explosion. In fact, since Darwin's time, what we have found as part of the Cambrian explosion is even worse, and what we found underneath the Cambrian is pretty bad for his theory, because we found fertilized sponge embryos, meaning that if there was some precursor, we really should have found it, but we didn't. It's just not there. We go from sponge embryos and possibly worms to all of these wonderful different types of organisms. However, this sudden emergence isn't the only time that you have really rapid development. The marine Mesozoic revolution, you have a sudden appearance of many aquatic animal types. Of course, the Cambrian explosion. The mammalian radiation, where when the dinosaurs died off, very suddenly you had all kinds of mammals. And then you also have what was called the Big Bloom, which is the origin of flowering plants. You went from an entire landscape that basically had no flowering plants to flowering plants being just about everywhere in a geologically short period of time. Okay, and so again, we have transitional elements for some spots in the fossil record, like Archaeopteryx looks like it could have been a transitional form. Then again, that it was found that birds existed prior to the earliest known Archaeopteryx sample or specimen, but it's assumed through a ghost lineage that Archaeopteryx came before birds. That notwithstanding, if we make those assumptions, then we have a couple of transitional spots. But again, the rest are largely drawn in. We do see a lot of commonality at the family, genus, and species levels. This is more observed in the present day and age that is supported. When you get to the order, class, phylum, kingdom levels, the connections are very much less reliable. So it looks like you can have change in organism within these three levels. I won't say easily, but is observable. But the higher changes are much less common in terms of actually finding evidence for them from the fossil record. Now, weakness number 4 is that it can be misinterpreted, right? The fossil record can just be misinterpreted. And the example that I have from my personal childhood is that when I was in grade school, the Coelenthicanth was thought to be a precursor fish that went from water to land. It had these big lobed fins that it was thought it used to kind of walk on land like a mud skipper, okay? Well, it turns out the Coelenthicanth is still alive today. It's kind of a living fossil, and it's a deep sea fish. It uses those big fins to ride hydrothermal currents, right? Cold water currents near the bottom of the ocean where it kind of just sails and glides. It never went anywhere near land, okay? So the evidence of this fish was entirely misinterpreted until they actually caught one, fishermen caught one. So, from NPR, here's another interesting example. Forget extinct, the Brontosaurus never existed. That was from December 2012. And then from Science Daily, Brontosaurus is back from April 17th, 2015. There was a period of time where the lovely Brontosaurus was thought to have just never existed. And then, oopsie, no, it's real. We really like it. We're going to bring it back. Really super scientific. Now, weakness 5 is an interesting one because it kind of changes the view of how we see fossils, or how I see fossils. Maybe other scientists would disagree with me. And that's the discovery of soft tissue. So from Science Daily, October 23rd, 2012, analysis of dinosaur bone cells confirms ancient protein preservation. And this is from North Carolina State University. And it says from the Science for Students, more dinosaur bones yield traces of blood cells and soft tissues. That was from June 24, 2015. And the scientist on that was Ashley Yeager. So soft tissue is being found more and more commonly, right? And when I say soft tissue, I mean like actual vascular tissue that still is elastic. They pull on it with a little set of tweezers and it recoils because it's still elastic. And I'm not going to go and say that this proves that life on Earth is young. That's not at all what I'm trying to say. There's a thinly plausible explanation that was thought up by that poor scientist I mentioned earlier, Dr. Mary Schweitzer. Apologies if I'm not pronouncing her name correctly. Who purified hemoglobin with samples in it and demonstrated over a 5-year period or so that it has a formaldehyde-like preservative effect. Thereby trying to say that in a large organism like Tyrannosaurus rex, blood pooling in a bone could have preserved the soft tissue as it was fossilized. The issue that of course, is that 65 million years is a really long period of time. And prior to her discovery, People treated her so viciously when she came out with it because no one believed that it could be possible. They never looked for it because it was never thought to be possible. So that's interesting. Everything else that I've read in the scientific literature points to a very old Earth. So I'm not saying this is de facto evidence the Earth is young or life on Earth is young. I'm just saying it was not expected. And its existence is still a consternation for people who want to say that people who believe that life is relatively young are total quacks, because this is one thing that sticks out against the, bookshelf of information that points to an old Earth, an old life being old on Earth. But what it does do, and I think this is pretty conclusive, is it kills the idea of uniformitarianism. So uniformitarianism was this idea that the present is the key to the past, that what is happening now is probably what happened in the past. And so when I was a kid, or when I was younger, fossils were thought to be made by a process of very slow sedimentation over time, where organisms died and sank down to the bottom and then were covered up by silt. And it happened over maybe hundreds of thousands, perhaps millions of years. These specimens were converted into fossils, right? Uniformitarianism, that's kind of the processes that are happening today. And that's how we thought must have happened back then. Well, when you find soft tissue in a bone, it means that bacteria in a relatively warm, shallow ocean, which is why we find these bones on land now, were not able to eat that soft tissue, which they really should have if the bones were left at the bottom of the ocean for a really long period of time. In fact, one of the main criticisms was that Miss Schweitzer hadn't found soft tissue, but really bacterial films, which turned out to not be the case, because bacteria should have eaten anything even remotely resembling an organic compound, a blood vessel or a red blood cell. Excuse me. Sorry, I've got a little frog in my throat today. So when any layer you find soft tissue in, basically validates or verifies the idea that that layer of sediment was laid down quickly. So it pretty well confirms catastrophism, the idea that the Earth has been shaped by a series of really catastrophic, horrible events. And any layer that you find soft tissue in is going to be a snapshot in time. So when you look at the geologic column as it's shown in many diagrams today, you would see this, right? You've got a continuous thing over time, millions of years ago, and it seems very nice and shapely, right? Like a continuous story being told. Well, any layer you find soft tissue, it could be a snapshot, and there could be an indefinite amount of time that passed in between that layer and the one above it. Sorry, especially if, every layer or the majority of layers turned out to be made by catastrophes, oh my goodness, and not slow sedimentation. So further studies are needed, and this soft tissue is being found in various places. So we're going to have to really reevaluate how continuous in terms of time the fossil record is, meaning that it might actually be a lot more fragmented than we thought. Weakness 6. So the idea of evolution is that life is kind of constantly changing due to environmental pressures. Well, we have things called living fossils. The coelenthecynth is an example of one that I just showed you. The comb jellyfish is another one. And this is a shot from a textbook that has multiple others. The ginkgo tree, the comb jellyfish, the nautilus, sea nautilus. Okay, these types of organisms, you have the fossil and then you have the real thing today. The fossil and the real thing today. And these have remained basically identical to what they are now for tens of millions of years. Okay, really long periods of time. And Darwin's theory doesn't really account for that, right? Evolution is supposed to be constant, things constantly changing, mutations happening constantly, and nature selecting for what's a little bit better, so that you have an organism like the box jellyfish that was around, I believe, 45 million years ago. Might be wrong, I'll double check that, come back to you. But it's one of the older fossils, and it's basically identical today. Is suspicious. It doesn't fit well with a constantly ever-changing kind of landscape. So those are some of the weaknesses of the fossil record. Oh, that's a lot, and we still have a little bit more to go today. So thank you so much for listening. I will see you all for the last of today's lectures very soon.